Equilibrium constant expressions. Now in the previous video we did look at the equilibrium constant here, the ratio between the concentration of the products and the reactants, but in this video we're going to encompass it within an actual expression law. So I just want to touch up on last time what we did. So last time, as time passes, reaction rate for the forward direction decreases, because of course the reactants are going to be used up in order to create the products. So then of course the reaction rate reverse increases this time. Therefore, they will eventually equalize. Why would they equalize? Because their slopes have equaled 0. In case you don't remember, I know we used NH3 and N2 and H2 last time. For this one, let's look at another example. Let's say we have NO2, nitrogen dioxide. Let's say it's this one over here, okay? And sorry, N2O4. Okay, dinitrogen tetroxide. It is going to start off as their reactant, and then as it becomes used up, as you can see, it is decreasing and the slope has flattened out to 0. As this is being used up, NO2 is going to be created and formed, and then like the last video with NH3, they also flattened out, so the slope also equals 0. So this here would be NO2. NO2 is the product. See how they have equaled out. So now, how do we derive an equilibrium constant from this concept? How to derive the equilibrium constant? And remember, equilibrium constant was this ratio between the concentration of the products, this one over here, and the reactants, this one over here. Well, let's start off with our K forward, okay? K here stands for the constant, okay? It's constant regarding the temperature that it's at. We did look in the previous video, again, link is in the description. Have a look at that prior to this video, because we did mention that K, the KQ, this will eventually turn into the KQ. It only gets affected based on one factor, which is temperature. So this here is at a constant temperature. Okay, so this here is the constant. So this K here, let's have a look at it from two perspectives, from the forward realm and then from the reverse realm. Okay, so let's first look at it from the forward realm. Okay, it is obviously the reactant. Okay, so this one here, it is going towards the right side over here. It is going to be the reactant though, because it is being used up. Also going towards the right, okay, is the NO2, but it is not being used up in the process initially. It is actually becoming formed thanks to this N2O4. So our K reverse is going to be for our product. So what are we gonna make a statement of this as? So this K forward for our particular reactant was what this one is over here. It is our N2O4. Okay, now I'm also going to be putting an EQ here. This stands for the equilibrium. So that is for this realm. I'm also going to do the same thing for this realm, K rev, and this is going to be for the product in question, which is NO2. And I'm also going to put an EQ because right now we're at equilibrium, okay? We're trying to always derive an equilibrium constant value when they are at equilibrium. The reactants and the products, they must be at equilibrium first. Now that we have done that, eventually they will equal out, right? So the slopes will equal 0, right? So we can actually start breaking this down further into this. So we have our K forward as being equalized with our K rev. So I'll write this over here, our K forward of our N2O4 is going to now equal the K rev, which makes sense because they're at equilibrium and they do eventually equalize. As we can see, it's proven over here based on that illustration of the graph. Now, to determine the ratio, this is what we're going to do. To determine ratio, we are going to now isolate just for the K. So this K over here needs to be divided. How? Well, this, if it divides itself, will cancel out, allowing this K forward to be isolated on its own. So that's what we're going to be doing. So we're going to write this out again, our K forward and our N2O4. But what I want to do is get rid of this. So we're just left with our K forward. Okay, you can do the same thing for your K rev, but for now we'll just look at for the K forward. You can just divide by our N2O4. You do that, they eventually cancel out. This is now isolated on its own. If you do it on the left side, you need to do it on the right side. So let's do it here as well. Let's divide it by this, what we just did. There we go. This is it. So our K forward is going to equal what? Our K forward equals our K rev, NO2, divided by our N2O4. Divided by our N2O4. Now, there is something very, very important to do here. Do not forget, for each concentration, it must be raised to the power equal to its coefficient. So I actually need to put a small 2 over here. How do I know that I have to raise to this power as opposed to any other number? Again, it's based on the coefficient. So if I were to get this out and write it out as an equation, our N2O4 here becomes our NO2, but remember, this is reversible, so it goes in either direction. So if you want to kind of change this so it kind of looks like that, you can do that too. It doesn't matter. Okay, now our NO2 here equalizes because it needs to decompose back into the N2O4 as well. So right now this is our chemical equation. Obviously it's not balanced, so let's balance it out. Well, if you put a 2 over here, now they're both balanced, the nitrogen and the oxygens. So for sure, this is our coefficient. So every time we look at a particular concentration, this concentration or this concentration, do not forget to raise to the power equal to the coefficient. This here has a coefficient of 1. So technically we have a 1 over there. You just don't see it. It's invisible, right? But for NO2, it has a coefficient of 2, so we must add that over there. I'm just going to bring this up over here. We're pretty much done. I just want to make a final statement. So technically, our K is equal to our concentration of the product divided by the concentration of the reactant. Now I do want to preface it here that if K is greater than 1, the equation is going to favor towards the product side, so the product formation is favored. If K is less than 1, reactant formation is favored. Similarly, let's have an example of small a and big A, small b, big B, and they are reacting to form, and again this is an equilibrium process over here, small c, big C, and small d, big D, can be represented as K is equal to, remember we just wrote out this expression here, our product concentrations on the top and our reactant concentration on the bottom, so our K is equal to our concentration of our C, but remember the C is going to be in capital because the coefficient here is represented as the power, okay, the superscript, okay, and then we have our big D over here, the small d on the very, very top, and then our reactant, same deal. There we have it. So what does this mean? So the ABC D, okay, all of these in capital, what does this represent? The ABCD represents concentration. Represents concentration. This obviously stands for concentration. Okay, this stands to represent. However, the small ABCD represents what? The coefficients, right? The moles. The coefficients. Now I also want to add some important notes here. The first important note is for you to understand and realize and to notice how when we have equilibrium, we are considering both the products and the reactant concentrations. This is important because, as you remember, in the rate law and rate law practice questions, we never considered the products. We only looked at the concentration of the reactants. Again, the link is in the description below. Quickly have a glance back at those practice questions we did. We only looked at the concentrations of the reactants. Whenever we are now tackling equilibrium questions, we need to be able to consider both, because remember, they are in a tug-of-war dynamic equilibrium fight with one another. So rate law only dealt with the concentration of the reactants. And for our second point, if this here is at equilibrium, so then we can put a small little KQ at the bottom there, okay? Whenever we have KEQ, and we'll look at a few practice problems on that, if that KEQ turns out to be greater than 10 to the 10, it will go to completion. However, if KQ is less than 10 to the negative 10, it will not react. I'll put this as a reaction. No reaction will occur. So pretty much what does this mean? Obviously only the reactants will exist. And lastly, if KQ is equal to 1, this means that the concentration of the products is equal to the concentration of the reactants. Let's have a look at some practice questions. Obviously, we want KEQ is equal to whatever our products are going to be divided by whatever our reactants are going to be according to their concentrations, right? However, we don't know if it's going to be at equilibrium just yet. Hence why in the previous example I didn't put KQ, I just put K. Okay, because we need to be at temporary equilibrium general formula first before we can figure out what it's going to be at equilibrium. So we're just going to put K here first as temporary. So let's put our products. We have our N2, our first product over here. There is no coefficient there, so it's just a 1, or you can just leave it out. And then our H2O, 2, ends up going up there. And then we're going to divide by our reactant. So our first reactant, our H2, it has a coefficient of 2. Let's put it up there. Same thing for our NO. There we have it. Now we have to make sure that our gases are going to be correct. Our N2 here is gas. Our H2O here is gas. Our H2 here is gas. And our NO is gas. This means that every single compound or diatomic molecule that we have within this expression are all going to be relevant and do not need to be canceled out. The only things that we need to worry about is if we see solids or liquids, they're considered pure, so they're going to have a constant value towards them, and we have to get rid of them. In this case, our gases are all present, so we have to make sure that we implement and make sure that they remain present throughout this expression. And if that's the case, we can put a KEQ over here because we realize it is now at equilibrium. We are finalized, so we can put that EQ at the very end. We have a sulfur trioxide gas that decomposes, so let's write it out. And it is decomposing into our sulfur dioxide gas and oxygen gas in an equilibrium reaction. Write the balanced chemical equation for the equilibrium reaction. We obviously don't have this balanced out. Let's try balancing. Pause the video, give it a try yourself. You should have gotten this. Now we can write out the equilibrium constant. So we'll start off with K, and we are going to get our concentrations. We have our SO2 over here to the power of 2, and we have our O2 to the power of 1, and then our reactants over here. We have our SO3 to the 2. We can just put our states. Notice how they're all gaseous. So this here is going to be a homogeneous equilibrium system. We don't have to cancel out anything else. We've figured out that this is what we have for equilibrium, so we'll just finalize it with a KQ permanently. Now let's try this question over here. We notice right away there that we have a liquid. Remember, the liquids and the solids are the ones we need to get rid of. So let's put our K. This is going to be temporary. And then we're going to put our concentration of ammonium ion. Oops. And it's going to be aqueous multiplied by our other concentration, also aqueous. And they do not have coefficients to worry about. And our NH3. Obviously, in order to get rid of this, you need to multiply it by a fraction. For our numerator here, it's going to be our H2O so that they can cancel out appropriately. So that we cancel this, cancel this. If you do it on the right side, you need to do it on the left side. So let's do it here as well. Now, we end up getting our K multiplied by that, okay? But remember, this thing here that we're trying to get rid of is considered pure. So we're going to actually implement it within our K so that it is now embedded as an equilibrium constant. So instead of just K now, we've rendered this being part of this K. So we're completely finished in terms of our temporary alignment. We can make this permanently as KEQ because we figured out that at the end of our system reaction over here that this and this are not part of it. So this is figured out now, so we can make this as a KEQ. We can blend them together, okay? So this here is our permanent constant now, that we have figured out, and then this one over here will just continue to be written out accordingly. As such, that's the answer. Let's finish off with this question. In a closed container, solid magnesium, so I'll write this out, it's going to be solid, and oxygen gas react. It's going to be an equilibrium process, so always put this one here, it can be forward or reverse, to form magnesium oxide. Okay, there we go. So obviously we know that this has a 2 charge, this has a negative 2 charge, that's why we've written it out this way. Now all we need to do is balance it out, putting a 2 over here, putting a 2 over here. That should be quite simple. Obviously this one is gaseous, sorry, solid, this one is gaseous, this here is obviously going to be solid as well. How do we know that? Obviously this here is a metal, it's going to be solid. This here is gaseous, so of course if you intertwine them together it's going to remain to be solid. Now we're going to put our K value. This is going to be our temporary value. We'll have to put it here, K temporary over there. Let's put our specific product. So we have our MgO, and this is going to be on the very top by our reactants. We have our Mg at the bottom here, also exponent 2. This is a solid. This here is our gas. No coefficients, we're not going to be putting anything up there. Seems like we're good, but remember, we have to get rid of our solids. Remember, solids and liquids we need to get rid of. So let's multiply this side by in our numerator so that they can cancel out appropriately diagonally. We need to do the same thing for this one. We're going to put it down here so that they can cancel out diagonally as well, because obviously both of these are solids. So our Mg over here cancels out appropriately. Do the same thing over here for the numerator. We just put in the denominator, that way that they can cancel out appropriately. So we're just going to be left with this. So now we know that it's no longer going to be temporary. We've now solved the equilibrium process here. We're going to be putting a 1 on the top here because there's nothing here anymore, right? So technically there's always a 1. This one here is a 1 as well, and then you just multiply by our O2 gas. Okay, if you want to get rid of this, you can, doesn't matter. So if you want to make this as a final statement, KQ is equal to 1 over our O2 gas. That's the answer. Alright, these are the 2 green questions of the day. This is the first one, this is the second one. Please give this a shot on your own. Pause the video and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.